So I'm Dr. Lutz Mary, working as an associate professor in the Department of Computer Science and Engineering in Rohini College of Engineering and Technology. The subject code is CS8088. Subject is wireless ad hoc and sensor networks. The core objective is to understand the various broadcast authentication protocols in wireless sensor network. Broadcast authentication protocols in wireless sensor networks. So what is broadcast authentication? In multicast, a single packet can reach millions of receivers. Through source authentication, receivers of multicast packets can verify if that packet comes from the correct source. The characteristics of wireless sensor networks: no central node, large scale, volatility of network topology, data-centric networks. Broadcast authentication. Why do we authenticate? To ensure a sender of the packet is indeed the sender and to make sure that the packet has not been tampered or changed along the way. How do we authenticate? So we can append a message authentication code to each packet that is transmitted. The packet format is where the MAC is computed using the shared key. So the P is equal to message will be concatenated with the message authentication code, that is the key along with the message. How it works? The symmetric cryptography in broadcast authentication. The problem arises when the receiver has the secret key. So now the sender's identity can be stolen. The trusted receiver can now make fake packets and impersonate the sender to other future receivers. Actually, we must look into the asymmetric cryptographic solution to provide us with a more reliable digital signature based schemes. So paradigms of broadcast authentication. Signing each packet will definitely provide secure broadcast authentication. How else does it provide? So overheading the time it takes to sign and verify, overheading bandwidth also. So it's broadcast authentication via delayed key exchange. So there are researchers in the field of wireless sensor network. They propose methods to eliminate overhead by using a single signature over all the packets that needs to be transmitted. The even methods that provide broadcast authentication via delayed key exchange have extreme vulnerabilities. So the denial of service attack, as you all know, that it can be introduced by overwhelming a receiver with a phony sender packets. Since the signature verification is computationally expensive, the receiver now left with authenticating meaningless packets. So how the security will be broken? So you have to know what is a hash function. A quick review of hash function. Hash function is a function that takes a string or message of any length as its input argument. A hash function produces a string of fixed length as its output, also known as message digest. An individual hash key, also called a digest, is a kind of signature for a stream of data that represents the contents. So the input is fox, the hash function, and we will be having the hash function based upon the hash key. The red fox runs across the ice. So the red fox walks across the ice, the hash function. So walks and runs, even though the message slightly differs, the hash function for that input varies. That's why it will be having the hash. One-way chains are widely used as a cryptographic primitive, especially in protocols need to commit to a sequence of random values. We can use a one-way chain to generate a string of length L by randomly picking the last element of the chain. So we then are able to generate a one-way chain by repeatedly applying a one-way function f to get our next value of the chain. So generate. So yes. So if you know the previous value, you can then only you can able to do the decryption. So one-way chains, to verify the element Si is the element at index I of a hash chain, we can check that if Si of I is equal to S0. In the more general case, Si commits to Sj if I less than j. So to verify Sj is part of the chain, while knowing, we simply compute if j minus I, Sj is equal to Si. So then if the condition holds, Si commits to Sj, in Tesla we want to reveal the chain in the order. How can we store the chain? So we create the chain all at once and store each element. But it requires storage and computation time. So we can just store L and then compute any other element of our chain on demand. And researchers have devised methods for efficient storage of one-way chains, such that one-way chain with elements log of n storage and log of n raised to the power n computation for accessing each element. Time synchronization. Tesla does not require strong time synchronization properties. The receiver only needs to know an upper bound of the sender's local time. We will denote the exact difference between the sender and the receiver time with delta. Since we are dealing with loose time synchronization, we are interested in the maximum time synchronization error delta, which is the upper bound of the exact difference. Difference sender receiver time. So since we are dealing with loose time, so I can say this is theta synchronization. We are interested in the maximum time synchronization error delta, which is the upper bound of the exact difference. So the receiver having their own time TR can compute the upper bound of the sender's time as TS less than or equal to TR minus T capital R plus TR. A note on security: when synchronizing the protocol, the receiver first records its local time T capital R and sends a time synchronization record to the sender. The time synchronization request contains a nonce, the heart of the security of our time synchronization protocol. If a hacker or an attacker could guess the receiver's nonce, then they would be able to send a time synchronization request to the sender with that particular nonce. The hacker then could replay the response later to the receiver. Upon receiving the synchronization request, the sender will respond its local time TS and replay with the signed packet that contains TS as a nonce. Sender setup: the sender has to divide time into uniform intervals of duration. The time interval the time interval 0 will start at time t0. At time interval 1 starts at time t1, where t1 is equal to t0 plus t interval. Time interval 2 will start at time t2, where t2 is equal to t1 plus time interval, and so on. The sender determines the length n of the one-way chain k0, k1 and so on kn. The length of our chain will determine the maximum transmission duration before a new one-way chain has to be computed. The sender picks a random value for kn. Using a pseudo-random function f, the sender constructs the one-way function f of k is equal to small fk of 0. The rest of the chain will be computed recursively using ki is equal to f of ki plus 1. The recurrence ki is equal to f of ki plus 1 yields ki is equal to f raised to the power n minus I kn, and it's because of this property we have the ability to compute any value in the key chain from the value of kn without having to know the intermediate results. At each k remains active over the interval I. Bootstrapping the receiver: the time interval, the sender is responsible for the key closure schedule. So when the key has to be revealed and ensures that the transmission of the following: the time interval schedule, the time interval ti, the starting t interval tint, starting time ti, the index of interval, which is the length of the one-way chain, key closure delay, which corresponds to the number of intervals. So the key closure delay d, which corresponds to the number of intervals. Finally, the commitment to the key chain ki is equal to I equal to j minus d, where j is the current interval index. Broadcasting the authenticated messages. At this time, the sender already knows which keys in our one-way chain correspond to the interval. The key remains secret for d minus 1 intervals, meaning that the message sent in the interval j will provide the ability to disclose the key k j minus d. The same key multiple times in the cryptographic operation k. Broadcasting the authentication messages: instead of using pseudo-random function f dash to construct the one-way function f dash is f dash of k, f dash of k of 1, we use f dash to derive the key to compute the MAC value. K dash of I is equal to f dash of ki. Broadcast a message ma in the interval. So see the diagram: to broadcast a message mji in the interval I, and construct the packet pj is equal to mj of, have to concatenate with the MAC value of k as well as m, that will be concatenated with the k I minus d. Authentication on the receiver side: the sender discloses a key. All parties have the access to the key. The attacker has to create a fake message and force the MAC. When the packets arrive, the receiver must verify MACs of the arriving packets were based on the safe keys. Yes, so what is a safe key? Safe key is the one that is only known by the sender, and safe packets that contain safe messages whose MACs are computed with safe keys. So sender sends the packet PJ at the interval I. When the packet PJ arrives at the receiver, they will use the self-authenticated key K minus D disclosed in the packet PJ to determine I. The receiver then checks the latest possible interval X that the sender could be in. So if X is less than I plus D, where D is a disclosure delay, the receiver packet is safe. Therefore, the sender has not reached the interval where it discloses the key Ki. The key So seal is randomly generated. Given a seal, the signer computes Fs is equal to Fs of 0, where Fs is a PRF. Fs in the commitment to S. Fs is authenticated to all possible verifiers using RSA signature or pre-distribution. The signer has to pre-compute the seal value. All seals are authenticated to all verifiers. So how to compute it? Compute hash of x hash h of m, where h is the hash function. Consider a hash function family gh whose value ranges is 0, n minus 1. Example g1 of x. So g of x such that 1, where g is a SHA-1, compute gh for all seals s1 to st, that is gh of s1, gh of s2 and so on. Look for a two-way collision of seals. gh of si is equal to gh of sj, with si and sj is a pair forms a signature verification. So compute hash h in such a way that h of m you have to verify s of I and s of j. Gh is equal to gh of si is equal to gh of sj. The security of the signature, where it comes from, the difficulty of finding the k-way collisions, the one-way functions. The asymmetric property of the signer has more seals than the adversary signature, can easily generate BIBA signature with high probability, while adversary cannot be able to tamper it. Exploits birthday paradox probability. There is at least one collision of the hashes of t random messages, approximately 1 minus e minus t multiplied by t minus 1 divided by 2n, where n is the range of hash function. The security of the signature lies, a signer will be having 1200 seals, an attacker will be having 10 seals. So will be having pins 7,62,460. It's a signature based scheme. The signer is not guaranteed to find the BIBA signature. The sign mh is equal to h, m of m such that c is a counter starting with 0. C is incremented if no signature is found. Compute gh for all seals, only s, and look k-way collision of seals. Verify signature. So verify k seals are distinct. Verify that they have the same image. So sender needs to authenticate potentially infinite stream of messages. Sender can only disclose a small number of seals before attacker would have to enough forged signature. The limit number of the messages that can be the signed solution. Sealed chains combination of seals and tests. So the possible questions are: so what is meant by broadcast authentication? You explain time synchronization in detail. So what do you mean by hash function? You explain the Tesla protocol with a one-way hash function. So discuss about BIBA authentication signature protocol.